Hello world, and welcome to this third video on my series about creating an IK-driven procedural walk animation. In this video, we're going to write a script to move our spider's body from side to side, as well as starting to write a script for our walk animation. My name is Marnie, and I make games. Okay, before we get started, I'd like to mention a few things. First off, the GitHub link, as well as the documentation link for spriteshape, and the asset that I used to create the background for the scene are all down in the description. I added a background as well as a ground object using spriteshape, so that we could actually see the spider's movement more easily and also judge how fast it's moving. So what do we want to achieve here? We want our spider's body to move from side to side according to its orientation. So we want our spider to move left or right, and if it's going up a hill, we want it to move accordingly. Let's start with that. We'll highlight our head, which is the main bone of our skeleton. And we'll go add component. We'll add a new script, which I've called movement. I've already added it here. Let's go edit script. Here's our movement script. I'll walk you through this. We have a serialized field for movement speed. This is basically the force that we're going to apply to get the spider moving. Then we have the maximum crawl velocity. This is the top speed of our spider, so not going faster than this. I've put this in to prevent the spider from continuously just gaining speed as we add force and flying off the screen. Then we have our current input. This will be a float value used to store the input from your keyboard, or later on if you use a controller to store the analog input from there. The parameters that I've put here, we will discuss later. These are related to the actual walk animation. Then we've cached the rigid body, which I've attached to the spider. And here we are setting the rigid body by using get component rigid body 2D. So in the update method, we get current input from input.getAxis horizontal. This will give us a value between -1 and 1. -1 being left, or left arrow in this case, and 1 being right. If our input is not 0, that means we need to do something. So we take our rigid body and check its velocity. We take the square magnitude of the velocity and compare that to the maximum crawl velocity. In other words, if the spider is going faster than its top speed, we should skip this step. If not, we grab the rigid body, add a force to it. The force will be a vector, which is basically in the direction of the transform.right for our spider. The size of it will be the current input times movement speed. Now let's break this down a little bit. So let's say our spider, for sake of simplicity, is standing on flat level ground. That means transform.right will be x1, y0, z0, which means there's no part of the vector pointing up or into the screen, the whole vector is pointing to the right. Our current input here will be either a -1 or a 1 or some value in between. The sign of this current input tells us whether or not our spider is going to be moving to the left or to the right. And then the movement speed is what we use to make this vector bigger or smaller. So let's say we have our movement speed set to 5. We would get a vector here of 1 by pressing the right hand key times x1, y0, z0 times the movement speed. So we'll end up with a vector of x5, y0, z0. If our spider was angled up, we would get something a little different. This would be along the lines of, say, x 0.7, y 0.5, and z will still be 0 because we're working in 2D. And that will move down the line and you'll get a different vector for your force that gets added to the rigid body. Now practically, it looks like this. If we go play, push to the right, our spider's body gets moved to the right, and if we push to the left, it gets moved to the left. You'll notice that it's currently very slow. That's because speed's not set to a very high value. Something else you may have noticed is that while I was in play mode, everything here went red. This is called Playmode Tint. I find it useful because sometimes we go into play mode and then we forget to exit play mode and we start changing values in our scene. And as soon as you stop being in play mode, everything you've done for the last 10 minutes goes away. I learned how to activate this from a video by a friend of mine called Midnite Oil. I've linked to the video in his channel. You should really check that out. He's got some great tutorials. Right. So now we have our head moving from side to side. Let's quickly just look at what I did to this. I've added a rigid body and I've frozen the rotation for our rigid body. This is quite important because if we do not freeze the rotation and we try to move, that happens. And now we no longer have a walking spider, but a rolling spider. Let's fix this. I also added a capsule collider. This basically keeps the spider's body from falling through the floor because the rigid body obviously is dynamic. When you've done this, you would also need to make sure that you have a collider on your ground level so that the spider also stays above ground. Otherwise, once more, spider falls through the floor. Right. Now, how are we going to get our legs to move? Looking at this, I want you to notice something quickly. When we grab the head, the spider moves, but the leg effector keeps trying to reach the IK target. Now this is exactly why we are using IK. But when we are walking, you want this IK target to stay here while the foot's planted. And then as soon as you get far away from this foot, you want the foot to pick itself up and move to a point under the body to balance. To achieve this, we need something else. We need a target position relative to the body that keeps moving with our body. So under the head, you can create an empty game object called placement targets, which is what I've done. And then for each leg, you can create a new placement target in the spot relative to the body you want it to be. Now, as we move the body, you'll notice that the placement target, which is this little blob in gray, keeps moving with the body. So what we want to do is to check. My body's moving, it's moving, and I'm getting further away from my placement target than I want to be. So I pick up my leg and go to the target. Now let's see what this is going to look like in a script. Firstly, let's grab our target. We'll go add component. And you can type foot mover or whatever you want to name your script and go new script. I've already prepared the foot mover script for us. So let's have a look at it. Here we have a serialized field that holds the transform of the leg placement target. That's our gray blob. And here we have a float for our step size. This is how big our steps will be, or in practical terms, how far the placement target will be from the IK target before a step is initiated. In update, we go vector2.distance, transform.position, which is the position of the IK target that this script is attached to, placement target.position, which is our placement target, and we check that against step size. So if we are further away than the defined step size, do move foot. Otherwise, do nothing for now. Move foot's pretty simple for now. We take our position and we change it so that it matches the placement target position. Or when we finished our script and saved it, remember to take the placement target and just drag it into this field here to assign it to this leg. Each leg should have its own placement target. For the sake of simplicity and clarity, we're just sticking to one leg right now. We've set our step size to 2. This should be 2 of these units. So what does this look like? Our step size is 2, which is basically 2 of these units. Now let's see when we try to walk. As you can see, our gray blob or our foot placement target moves with the body. And as soon as it gets 2 units away, the IK target jumps to it and we have a step. This is a pretty horrible step because it's basically an instant shuffle. That's something we can fix. But first, there's a different issue we need to fix. Notice here that if we move to the right, away from our current position, the leg overextends. Now this is because we've got a big step. But if we go this way, the leg actually goes under the body, but not to such a severe degree. Now, if you think about when you are walking, you are constantly trying to keep your weight over your foot. That means falling forward onto the foot that's stepping forward and adjusting accordingly. Now, this isn't so hard to fix. What we would want to do is shift this position forward by just a little bit or backwards a little bit, depending on which direction we're moving. So if we're planning to move this way, it would be good to just advance this a little bit so that when the body eventually gets here, the leg will step out onto a position that makes sense instead of ending up almost behind the body and having the spider fall on its face. The same applies for the other direction. Small advance this way. So how do we do this? Well, we've already arranged our placement targets under a single parent. So we can just advance this parent a little bit depending on our direction. What does this look like in our movement script? Let me show you. So here in the movement script, you'll remember that I had a parameter for the foot placement targets parent, which we'll assign in the editor. And we have a vector2 that stores its initial position. Now this initial position is actually the local position. So in start, we take initial position, which is a vector2, and set it equal to the foot placement target parent assigned to this body, and we grab its local position. Now, what's the difference between a local position and global position? The local position is relative to this body. So in other words, if this is 2.5 units down and 1.5 units to the left, that means the local position will be minus 1.5x and minus 2y. But the world position, well, I'm not sure where my origin is right now. Let's just grab this. The world position here currently is 1.69x. In other words, from the 0 point, it's 1.69 units to the right, and it's also 0 units up. Now what happens when my head moves and the foot stays in one place? The local position has now changed because it's further to the left from the head, but the world position has stayed the same. For this, it's stuck to its local position because it is parented to the head. Okay, back to the script. So in our script, we've set our local position so we can work relative to the body as a initial position or as a vector2. And then when we check our input, we want to take our foot placement parent's local position and we want to set it to a new position, which would be equal to the placement target initial position. So in other words, our neutral 0 position for it. And we add a vector2, which is in the direction of the right-hand side of our spider, times the current input, in other words, positive or negative, so left or right, times the foot placement target advance. This is a parameter we've set here. All that basically does is say, okay, if our input is 1, move, in this case, 1 unit forward. We could have made this 3 or 2. 1 makes sense at the moment. If it's minus a half, then you move this times minus a half to the left. So what does this look like practically for us? Let's go here. For the purpose of illustrating the problem, I made that 0, so let's push that up to 1.5. And look at what happens. You can see each time I press the left button, the local position for my placement target moves to the left or to the right. And this needs a little bit of tuning. I might have made it too big. But this is already a great improvement over what we had. Okay. In our next video, we're going to be working on that walk cycle and getting a proper walk animation going. Until then, I'm Moni, and I'm saying goodbye.